Hello friends, in our last session we have discussed the routing functionality of network layer and we have also explored the link state algorithm. Now we will discuss about another routing algorithm, that is distance vector algorithm. A global or centralized routing algorithm computes the least cost path between source and destination using complete global knowledge about the network, as we have seen in the Dijkstra's link state algorithm. Whereas in a decentralized routing algorithm, the calculation of the least cost path is carried out in an iterative and distributed manner, as in case of distance vector algorithm, which we'll explore now. Unlike the link state algorithm, which uses global information, the distance vector algorithm is distributed, iterative, and asynchronous. It is distributed in that each node receives some information from one or more of its directly attached neighbors, performs calculation, and then distributes the results of its calculation back to its neighbors. It is iterative in the sense this process continues on until no more information is exchanged between the neighbors. The algorithm is asynchronous in the sense that it does not require all the nodes in the network to operate in lockstep fashion with each other. We will see that an asynchronous, iterative, self-terminating, distributed algorithm is much more interesting and fun than a centralized algorithm. Before we dive into details of the distance vector algorithm, it will prove to be beneficial to discuss an important relationship that exists among the costs of the least cost path. Let dxy be the cost of least cost path from node x to node y. Then the least costs are related by the celebrated Bellman-Ford equation, which is given as dxy is equal to minimum of v c of xv plus dvy, wherein minimum v in the equation is taken over all of the x neighbors. dy dvy is the v's estimated least cost path to y, and cxv is the direct cost of link from x to v. The Bellman-Ford equation is rather intuitive. Indeed, after traveling from node x to node v, if we then take the least cost path from v to y, I repeat, indeed after traveling from node x to v, if we then take the least cost path from v to y, the path cost will be cxv plus dvy. Since we must begin by traveling to some neighbor v, the least cost from x to y is the minimum of cxv plus dvy taken all over neighbor v. Before moving further, we will first check out the validity of Bellman-Ford equation by taking an example. We will check it for the source node U and the destination node Z as illustrated in the figure. Here the source node is treated as U and Z is treated as the destination node. The source node U has three neighbors node, that is node V, node X and node W, as there is a direct link between these three nodes from the source U, UV, UX and UW. By walking along various paths in the graph, it is easy to see that DVZ, it is a cost from node V to Z, is 5. Is shown is V DVZ. 2 plus 1 plus 1, that comes out to 5. Next, cos dxz is 3. From node X to node Z, dxz, that is 2 plus 1, it is 3. And dwz, that is from node W to Z, is 1 plus 2, that is 3. Putting this value into Bellman-Ford equation along with the cost CUV plus CUX plus CUW, which is CUV is given as C cost, direct cost from U to V, U to V is 2, direct cost from U to X is 1, and direct cost from U to W is 5. After substituting the value of all these variables, comes out to be 2 plus 5, 1 plus 3, 5 plus 3. We need minimum of all these three values, which comes out to be 1 plus 3, that is 4. Hence, DUZ, that is the minimum least cost path from U to Z, will be from U to Z is 1 plus 1 plus 2, that is 4. Hence, we can say that Bellman-Ford equation is valid. The basic idea of working out distance vector algorithm is each node X begins with dx of y, an estimate of cost of least cost path from itself to node y for all nodes in set n. For each node X, the distance vector algorithm maintains the following routine information. For each neighbor node V, the cost CXV from X to directly attached neighbor V. Node X distance vector, that is dx for dxy for all y in n, containing X estimate of its cost to all destinations y in n, and the distance vector of each of its neighbor V, that is dv of y for all y in n for each neighbor V of the X. In the distributed asynchronous algorithm, from time to time, each node sends a copy of its distance vector to each of its neighbor. When node X receives a new distance vector from any of its neighbor V, it saves V's distance vector and then uses Bellman-Ford equation to update its own distance vector as follows. That is, dy of x is equal to minimum v c of xp plus dv of I for each node y in n. If node x distance vector had changed as a result of this update step, Node X will then send its updated distance vector to each of its neighbor, which in turn update their own distance vector using again Bellman-Ford equation. Here, as long as all the nodes continue to exchange their distance vector in an asynchronous fashion, each cost estimates dxy converges to small dxy, that is the actual cost of least cost path from node X to node Y. In distance vector algorithm, each node of the graph may be in either of the three states, specifically the wait state or the recompute state or the notify state, and continuously thus transmit from one state to other. In wait state, each node waits for changes in its local link cost of change message from its immediate neighbors. In recompute state, upon occurrence of change either in its own local link cost or message from its neighboring node, it recomputes the distance vector accordingly by taking into consideration the latest updates. In notify states, once new distance vector is computed, it will notify the changes thus occurred to all its immediate neighbors. Distance vector algorithm is iterative in the sense that each new iteration of computing new distance vector is triggered by either local link cost change or distance vector update message from neighbors. Distance vector algorithm is asynchronous, means distance vector recomputing and updates are either not occurring simultaneously across all the nodes nor controlled by any centralized mechanism. Rather, it is triggered at individual nodes as and when there is a changes in local link cost or upon receipt of change message from its neighboring nodes. It is purely work in distributed or decentralized mode. We call that the link state algorithm is global algorithm in the sense that it requires each node to first obtain a complete map of network before running the Dijkstra's link state algorithm. Whereas in distance vector algorithm is decentralized and does not use such a global information. Indeed, only information a node will have is the cost of the links to its directly attached neighbors and the information it receives from these neighbors. Here, each node waits for an update from any neighbors, calculate its new distance vector when receiving an update, and distribute its new distance vector to its neighbor. Though recomputing the distance vector is iterative process, but definitely it is a self-stopping. That is, iteration is triggered only on certain instance like change in local link cost or change message from the neighbors. In absence of these two triggers or events, no action is taken. Hence, it is self-stopping in that sense. To have a better insight into the working of distance vector algorithm, we will explore one simple example with only three nodes x, y, and z as seen in the figure on the right side. of the screen. This is a sample network consists of 3 nodes X, Y, and Z with their respective initial link cost. This is 2 is the link cost in between node X and Y. That is the link cost associated with link XY. 7 is the link cost associated with XZ, and 1 is the link cost associated with Z and Y. Here, this particular column displays the 3 initial routing tables for each of these 3 nodes X, Y, and Z respectively. Here, this blue color is used to indicate node X. Here, this is a routing table, initial routing table for node X. This is an initial routing table for node Y. And this is an initial routing table for node Z. Within a specific routing table, each row is a distance vector. Specifically, each node's routing table includes its own distance vector and that of each of its neighbor. Being there are 3 nodes, first row is in this case for node X, the first row is distance vector for itself, and these 2 rows are distance vector for node Y and node Z. Thus, the first row in node X is X initial routing table, that is dx. It is dx of X, dx of Y, and dx of Z. That is 0, 2, and 7. Hence, the value 0, 2, 7 comes here. Second and third row in this table of node X are the most recently received distance vector from node Y and node Z respectively. Because we are at the initialization stage, at initialization node X has not received anything from either node Y or node Z. Hence, the entries in the second and third rows are initialized to infinity. Since we are about to start the algorithm, initially node X does not receive any updates from node Y and node Z. Hence, the value in distance vector value for node Y and node Z are initialized with infinity. Similarly, for node Y, hence as it has not received anything from node X and node Z, hence these 2 rows are initialized with infinity, and the initial distance vector of the node Y itself is 201, that is dy. dy of X, dy of Y, dy of Z, that is 201. dy of X, dy of X is 2, dy of same is 0, and dy of Z is 1. That is 201 is the initial distance vector of node Y itself. And similarly for node Z, first 2 rows as associated with nodes X and Y has not received any updates from node X and Y, hence initialized with infinity, and the initial distance vector for the self node Z is 710. After initialization, each node sends its distance vector to each of its two neighbors. Once the routing table is initialized, after initialization, each node sends its distance vector to each of its 2 neighbors. This is illustrated by animation. Updating router table or forwarding table entries from first column of the table to the second column of table. For example, here after initialization, node X sends its distance vector, that is 207, to its neighbor Y and to its another neighbor Z. Initially, The first row in node table was initialized with infinity, but after initialization, node X sends its own distance vector to the two neighbors. Hence, this row is changed from infinity to 207. And similarly, at node Z, the first row is replaced by the initial distance vector of node X. Similarly, node Y will send its own distance vector to its own neighbor. Node Y will send to node X and node Z. And node Z send its own distance vector to the remaining two neighbors, that is node X and node Y. This is the condition once all these three nodes sends its own distance vector to their neighbors. After receiving an update, each node recomputes its own distance vector. As each of these two nodes receives an update from other nodes, after receiving updates, each node recompute its own distance vector. For example, at node X recompute its own distance vector, which was earlier 2027. After recomputing, it comes out to be dx of x is 0, dx of y is computed as 2, and dx of z is computed as 3. Hence, it recomputed its distance vector and it replaces an update with the newly computed value, that is 0, 2, 3. Second column therefore displays for each node the node's new distance vector along with distance vector just reduced from its neighbor. This second row particularly displays the recently received updates from the other neighbors as well as the currently recomputed its own distance vector. Note, for example, that node X estimate for the least cost to node Z, that is dxz, has changed from 7 to 3. Here, this value is changed from 7, dxz is changed from 7 to 3 after the computing. Also note that for node X, neighboring node Y achieves the minimum. That is, neighboring node Y has achieved the minimum. After the node recomputes their distance vector, they again sends their updated distance vector to their neighboring if there has been change. Here, since here there is a change in the distance vector of node X, it will send the updated distance vector to its neighbor. That is, it will send the updated value of its own distance vector to neighboring node Y and neighboring node Z. Updating router tables or forwarding tables entries from second column to third column and so on. Note that only node X and Y sends update. Wherever there is a change, the change has been updated. As there is no change at node Y, it will not send any detail to the other neighboring nodes. After receiving the updates, nodes then recompute their distance vector and update their routing tables and so on. The process of receiving updates distance vector from neighbor, recomputing routing table entries, and informing neighbors of the change cost of the least cost path to a destination continues until no update message are sent or received from the neighbors. At this point, Since no update messages are sent, no further routing table calculation will occur and algorithm will enter in the wait state. That is, all nodes will be in the wait state. The algorithm remains in this wait state until there is a link cost change at any of the nodes. This is how distance vector algorithm works. Here we have covered the details of distance vector routing algorithm with one example. In the next part, we will explore yet another example of distance vector algorithm for better understanding. Thank you.